Whew. Thank you. All right, looks like another lonely day, sir. But we do have people joining us via the stream, so that's nice. Let's go ahead and get into it. Oh, Jacob sent me an email. All right. So what we've been doing in statistics so far is trying to measure our data and understand some overall aspects of it. However, if we really want to know our overall data's trend and what we can expect from the data points in between the points that we have, things that we don't have, fill in the blanks there, then what we want is a model. We want to be able to predict what our data is going to do, okay? So there's several different models out there for fitting data, the most simple of which, though, is the linear model. So you've probably seen this in high school already. Y equals mx plus b. This is our linear model. And again, it's the most simple model that we can use to fit data. Not all data is going to fit this model at all, though. And some is a lot more complicated and just won't be able to fit into this model. But there are a decent amount of sets of data out there that work with this. So let's go over this real quick. First of all, in this model, we have two variables, y and x. What we will typically do with this is we'll plug in a number for x and then multiply it by m, add b, and it will give us y. This means that y is dependent upon x. So we can call y our dependent variable. And in turn, that means that x is our independent variable. It doesn't matter what we plug it in. Nothing's going to change x. We can plug in whatever we want for it. Okay, so again, y is our dependent variable because it's dependent upon what x is, and x is our independent variable. It's just what we're going to be plugging in and seeing what we get out. M is our slope. M tells us two things. One, it tells us if the data is increasing or decreasing. So as we plug in higher and higher numbers for x, so as x increases, does y increase also, or does it decrease? And the slope can tell us that. The other thing that slope tells us is how fast it increases or decreases. B, this last number here, is what's called the y-intercept. And for a lot of these models, that's going to be where our data starts. Not all of them, but typically we can think about this as where our data starts. And I'll get into that a little bit later. Now again, this is what you probably saw in high school algebra. For statistics, we actually have another version of this model. It's basically the exact same thing, but it's y equals b sub 1 x plus b sub 0. So it's the exact same thing. Y is still our dependent variable. X is still our independent variable. X is still a thing we're plugging in. B sub 1 is replacing m, so this is our slope. It's the thing that's going to tell us how much we're increasing or decreasing. And B sub O is our y-intercept, or where we're starting. Okay? So when we're using these models, what we're going to do with them quite a lot is use them to predict other data points. So we might have a group of data, but if we want to predict what that data would look like further on down the line or in places that we don't have data, we can use these models to get those points. And often that's going to be with a graph. So a graph, again, is a great way to visually understand data. And so in this case, it shows us visually what the data is doing overall. And we graph these models on what we call a Cartesian grid. Cartesian because the person who came up with this grid type is named Descartes. He was a French mathematician. Just give me a minute here. I gotta answer someone's request. Okay. Sorry about that. So again, this is called a Cartesian grid. And the basic idea behind this is that since we have x and y, and they could be any number, we need a way to plot x and y. So this horizontal line right here is what we call the x-axis. And the vertical line is the y-axis. And they're both number lines. Again, we want to be able to see where they fall on a number line, what these values look like on a number line, and compare them to the other value. So, just like any other number line, we have 0 in the middle, positive numbers on this side, negative numbers on this side. So like for our x-axis, it might look like, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then the last one is 10. And then on the other side, negative 1, negative 2, negative 3, negative 4, negative 5, negative 6, negative 7, negative 8, negative 9, and the last one is negative 10. Again, it's just a number line, so from negative 10 to positive 10. Okay? Y-axis, it's the same thing. It's another number line, but instead of being horizontal like we're used to seeing number lines, it's vertical. So positive numbers up here, negative numbers down here. And again, it would be something like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And I'll fill in the negative ones down here. Okay. So when we start working with these models, again, what we're going to be doing is we're going to be plugging in numbers for x and seeing what we get out for y. So let's say that we plug in 5 for x. So 5 right down here for x. And we get 6 out for y. Well, what we do is we find 5 and then go up to 6 on the y-axis, and we put a point here. Again, what these are doing is they're comparing distances. So how far out do we have to go on x? How far out do we have to go on y? And when we compare them, they get to a particular point in space. Maybe we plug in a 3 for x and we get a 3 out for y. Now, seeing these, if we have enough points, we can eventually connect those points together and get a line. This line represents all of the points that are possible from this model. So then we could maybe say, okay, what happens if we plug in a 6 for x? Well, if we go up to our line from 6, we can then go over and it's going to be about 8. If this was, an actual like computer or graph paper or something, not just me writing down numbers, it'd be a lot easier to read. But again, you could plug in 6. Okay, what do we get for 6? I don't have to calculate it. I just have to look at the graph and see. Does that make sense? Okay, so these models, again, allow us to predict what data is probably going to look like. Now, Data's a funny thing, and really, when we do plot data on a grid like this, it's not always going to fit our line exactly. It might be kind of off the line. There might be some that fall directly on the line, but for the most part, it's going to be kind of scattered. However, if we make our model correct, we can get a model that is pretty close to what the data does. And so again, we can predict what it's going to look like. We might not be exactly on what the actual data happens to be in real life, but we can predict it. We can get close. Kind of like with predicting weather. So, the weatherman says there's a, 50% chance of rain today. Well, that means it's a very strong chance for rain, but it might not rain today. He's just telling you how likely it is that it's going to happen. Okay? So that's what these models are doing for us. They're letting us predict what the data is probably going to look like, even though we don't have the actual data yet. Okay, does that make sense? All right. So let's go ahead and make a model for ourselves. The example I've been using today is maybe we have a phone company who has a plan for their subscription service, and each month you're going to pay a base fee of $25. Okay? So it doesn't matter what else you do, you're going to pay at least $25 a month. And then they'll usually also charge you per minute of phone usage. So price per minute. And let's say that for this phone company, it's something like 20 cents per minute. Okay? Now remember that our model that we're trying to make this fit into is y equals b sub 1 x plus b sub o. So let's think about what this model looks like in terms of this phone subscription. So what we want to know is the bill, and that's actually what this is going to tell us, is if we do the calculations over here, y will be the bill. So that's the outcome. So we already know that. That's what this model is trying to tell us, is what the bill is. X, again, is what we're plugging in to figure out what y is. Y is dependent upon x. So if we're plugging in numbers for x, it's variable. It's changing. The initial fee is not going to change. This is one of our constants. The price per minute is not going to change. It's, again, a constant. X is the thing that can change. So if we're thinking about this bill is based off of how many minutes we use the phone. So what's changing in this bill? What's the minutes that we use in the phone? So our x, that independent variable, is minutes used. Making sense so far? Okay. Now these other two, these constants, have to fit in somewhere in b sub 1 and b sub 0. So again, x is the minutes that we've talked on the phone. And what do we see next to x? X times b sub 1. So if this is the minutes and we're paying a price per minute, b sub 1 is our price per minute. It's how much we're paying for each of these minutes. So b sub 1, we will say is 0.2, or the price per minute. which leaves us b sub 0, which is the initial fee. Which you can imagine if we didn't use the phone at all 1 month, that means we have 0 minutes. 0 times b sub 1, anything times 0 is 0. Then 0 plus 25, 25. So no matter what, we have to pay that initial fee of $25. So yeah, b sub 0 is 25. So let's put this all together. This means we have y equals 0.20 times x plus 25. Here's our model. Now, how closely is our data going to fit this model? Unless the phone company is a bunch of jerks, then it's going to fit exactly. You know, it shouldn't vary from this model, unless the phone company is doing something skeezy. So let's go ahead and try some things out with this model so that we can understand it a little bit better. So again, the model we just came up with was y equals 0.20x plus b. I'm sorry, not b, 25. Hey, that works. So let's plug something in for x and see what we get. Maybe we use 150 minutes in a month. Okay, so let's plug that in. That means we now have y equals 0.20 times 150 plus 25. And notice that I used parentheses around 150. Anytime that you plug a value in for a variable, so in this case 150 in for x, you want to use parentheses. The reason for that is because these parentheses preserve operations. So first of all, operations are things like add, subtract, multiply, and divide. And preserving them means that whatever we're doing up here, we're doing the exact same thing down here. So up here we have 0.2 times x. This had better still be 0.2 times x, which it is. 0.2 is multiplying by 150 because whatever we have directly on the outside of parentheses multiplies to those parentheses. You can imagine if instead we had negative 150 and we didn't use parentheses, this would look like 0.20 minus 150, in which case we wouldn't be doing the same thing. We're supposed to be multiplying, but if we didn't have those parentheses and there was a negative, it'd look like we're subtracting. So we want to make sure we use parentheses when we plug things in for a variable. All right, well, we've got it all set up. All we need to do now is calculate it. So, always follow your order of operations. That's parentheses, exponents, multiply, divide, add, subtract. So parentheses. We have parentheses, but it doesn't look like we can do anything inside of them. It's just a single value, so we'll skip that. Exponents. I don't have any exponents. There's no squared or cubed or anything like that, so we'll skip it. Multiply. We definitely have multiply going on. We have 0.2 times 150, so let's go ahead and figure out what that is. I got my calculator here. 0.2 times 150 is 30. So we will rewrite our model, or our equation. Now we have y equals 30 plus 25. Pretty easy to figure out what we need to do now. Just add those together. So 30 plus 25, we get y equals 55. So if we use 150 minutes in a month, our bill comes out to be $55. Make sense? Good. So as a point on a graph, that would be 150 for our x and 55 for our y. We'll come back to that in a minute. Okay, let's do something slightly different. We won't always have something to plug in for x. Maybe instead what we have is just the bill, and the bill doesn't tell us anything except for how much we owe, which is kind of a crappy thing to do for a bill, but maybe that's what they're doing. So maybe we just get a bill in the mail and it says, you owe $300. That's a lot of money to pay. That's an insane phone bill. Now maybe I know how many minutes I used that month, but I want to know how many minutes this would represent, and then compare the two. So we would plug this into our model. Except now, instead of plugging in something for x, we're plugging in something for y. So we're plugging in the 300 for y. Then we have still 0.20 x plus 25. Now this model is set up to find y really, really easily. All we got to do is plug in something for x, do some math, and we find y. This one, again, it's set up to find y, but we already have y. We want to find x. It's not set up to find x all that easily. However, it can still do it. We have to play with it a little bit, though. So the reason it's so easy to find y in this model is because y is by itself. If we can do the same thing with x, get x by itself, we can find it very easily. So the goal here is to get everything away from x. So if we want to solve for something, we want to get everything else away from it so we just have that variable. That's the idea behind solving. So we want to eliminate all the numbers that aren't x. How do we do that? Well, we do the opposite of what the numbers are doing right now. So for instance, 0.2 is multiplying by x. The opposite of that would be to divide by 0.2. This 25 is adding to x. The opposite of that would be to subtract 25. And we can start by doing either one of these. It really does not matter. Though one way is more easy than the other. So think about this. If we were to start by dividing 0.2 off of this x, whatever we do, we have to do it to the entire side. We can't just pick and choose what numbers get to be multiplied or divided. So if we're going to divide this 0.2 off, we have to do it by the entire side. So yeah, dividing 0.2 off would cancel the 0.2 here, but we'd also have to divide 25 by 0.2, and that sounds like a lot of work. However, if instead we start with subtracting 25, so the entire side is getting subtracted by 25. Well, when we add and subtract, we can only add and subtract like terms. 25 and negative 25 are like terms. We can subtract that. 0.2x and 25 are not like terms. This one is in terms of x. This one is not got an x on it. We cannot subtract that from there. So we only have to worry about that. We don't have to worry about subtracting anything from this because it's not a like term. So 25 minus 25 cancels. The other thing you need to keep in mind, though, is whatever you do to one side, you have to do to the other, because an equation shows perfect balance. And we want to make sure that this thing stays balanced. So if we subtract 25 from one side, we have to do it to the other side as well to make it balance out. 300 minus 25 is 275. And what we have left on this side is 0.2 0.20x. Okay. Now, we have just the 0.20x, and so if we divide it, we don't have to worry about dividing anything else. So their opposites, they cancel. We have to do the same thing to the other side to make sure we balance things out. So nothing's left on this side but x. So good, that's what we wanted to do. Now we need to do 275 divided by 0.2. So 275 divided by 0.2 is 1,375. So that means that if we have to pay a bill of $300, then we would have had to talk for 1,375 minutes. It's a lot of minutes. In fact, I think that's like 60 hours. Let me see. Divide by 60. No, that's like, I was off. That's like 23 hours. It's almost an entire day of talking. Okay, the idea here though with solving is that you kind of want to go backwards through your order of operations. Do your add and subtract first, so cancel out any add and subtract, then cancel out any multiply and divide, so on and so forth. Parentheses you still want to do first though. Okay, but we see here that if we were to make this into a point, x is 1,375, y is 300. So looking at these 2 points, we can kind of figure something out about this model here. As x increases, so like from 150 to 1,375, y also increases. So this model is showing an increasing trend. Okay? And that makes sense. Like again, I said, m, which is this number right here, tells you what direction the model is going. So is it increasing or decreasing? And the way you can tell easily by looking at m is it positive? If m is positive, it's increasing. If m is negative, it's decreasing. And then the number itself tells you how fast it's increasing or decreasing. So let's go ahead and look at that on a graph. Any questions before we move on though? Okay. So let me make a graph real quick. Okay. So I'll put some numbers on here. 15, 19, 20, 21, 22, 23, 24, 25, 30, 35, 40. Okay, so I've got 1 through 40 here. I'm going to do the same on this side. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, Again, 1 through 40 on this one. So our model says y equals 0.20x plus 25. 25, damn it. So if we want to graph this to see the overall behavior of our model here, we first need a point that we can graph, just any point. And the easiest way to do that is with our y-intercept. Again, this number right here is where the y, or where the graph crosses the y-axis. Another way to think about it is, if we plug in 0 for x, 0 times 0.2 is 0, 0 plus 25 is 25. So 0 for x is right here, 25 is right here. There's our first point. It's kind of hard to see, but right there. Now to get the rest of our points, we can use the slope, because again, it tells us if it's increasing or decreasing and how fast. So we know it's increasing, but we want to know how fast. Best way to do that is to convert this decimal into a fraction. So 0.2, that's 2 in the tenths place, that means it's 2/10, is simplified to 1/5. So 0.2 is 1/5. And you can read this fraction to see how far you go in both directions. The top is how far you go on the y, the bottom is how far you go on the x. So again, we know it's increasing, so what this means is we're going to go up 1 on the y and over to the right 5 on the x. Make sense? Okay. So to get to the next point, we go up 1 on the y, over 5 on the x. That's right there. Next point is up 1 over 5, right there. Up 1 over 5. Up 1 over 5. Up 1 over 5. And so we've got this line coming out here. So, again, now that we have this graph, we can actually just predict what the rest of our points would be. We don't need to calculate anything else. We don't need to gather more data. We don't need anything like that. We can just extrapolate it and predict it from this graph. So, for instance, let's see, 5, 10, 15, 20, 25, 30, 35, 40. If we did 40 minutes, that would get up to here. Okay. What would that represent on our y? Okay, so 40 times, I just want to make sure I get this correct. There we go. And plus 25 equals 2. Yeah, so here's 25, 30. This is 35 here, so 33 is right there. So when we have 40 in for x, we have 33 on our y. And we can just get our data points that way. Again, though, this is a prediction. And in this case, since we're talking about a phone company and their billing plan, it should always fit this line. Real data won't always do that, though. Another thing to note about this, though, can we ever have negative minutes? So these are all positive minutes, but can we ever have negative minutes? Can we talk for a negative amount of minutes? No, we can't. Will the bill ever be less than $25? No, at the base price, it's always going to be 25. Even if we talk 0 minutes, we still have to pay $25. So what we can see from that is that, well, none of this is useful, and anything below this is not useful, so this whole part of the line in a real world situation doesn't work. Okay? So this is just extraneous information. Theoretically, our model still says that there's points back here, but in the real world, that doesn't matter. We only want to know what in the real world would work, since this is a real world application. Okay? Does that make sense? Good. All right. Any questions? All right, one more thing I want to show. Where's that page I had? Need to look through my notes real quick. There it is. Real data, like I said, is not always going to fit our line. We can predict, and hopefully our data is going to be pretty close to what we predict, but this line is not going to be definitive. It's not going to be, this is the be-all, end-all, only data can fall on this line. Sometimes data can fall around it in the real world. So we can predict it, but we're not always going to be exactly right. For that, we need to adjust how we model this data. So we can predict data, and then collect real data, and then compare our predicted data to what the data actually came out to be. So here I've got an example of that. This is our predicted and our real. So we predicted 5, 10, 15, 20, 25. But the real data that we collected came out to be 3, 11, 12, 19, 27. It's close, but it's not quite right. So what we need to do is we need to start getting some numbers to represent how far off this real data is from our predicted data. So what we do is we subtract each of these numbers to see how far they off are from each other. So 5 minus 3 is 2, 10 minus 11 is 1, 15 minus 12 is 3, 20 minus 19 is 1, 25 minus 27 is 2. Okay? And we can get a mean for that. That would be our, then we square those numbers. So 2 times 2 is 4, 1 times 1 is 1, 3 times 3 is 9, so on and so forth. And then we can get a mean for that. That's our mean square error. We can also do a sum of squared errors. That would be this 19 down here. And these two numbers help us understand how we need to adjust our model to more closely fit the actual data. Okay? And that's what we're going to be getting into next week. Also next week, we're going to be having a test. It'll be our first test of the semester, and I'll be giving that on Friday. This weekend, probably later today, got the hiccups. Probably later today, I'm going to be giving out a review through email that'll hopefully help everybody to study for the exam on Friday. Okay? But I think that'll do it for today. So I will see everyone on Monday, and I hope everyone has a great weekend. And thank you for coming to class, by the way.